Welcome back everyone to this video on relations. So this may seem a little abstract because it is, but we need this language in order to be able to talk about functions. So obviously functions are extremely important. You've seen those, ever since you started doing algebra in high school probably. This is going to be critical for the things we're going to be building up to when we talk about the theory behind calculus. So this is sort of the theory behind functions. So first off, definition. If you have two sets, A and B, then we can make a new set that consists of ordered pairs. So every element of this new set, A cross B, or A times B, right, will be an ordered pair where the element in the first slot, right, will come from the first set, say A, and the thing in the second slot of the ordered pair comes from B. Right? So you've seen ordered pairs before, of course. When you plot graphs, you would have a number like 2 comma 3 that you would plot on the graph, and maybe the first coordinate we would use for x's, the second coordinate we'd use for y's. You don't have to do it that way. In general, this could just be any way of matching up elements from different sets. But the notation is at least what we want to get out here, because we'll be writing down lots of stuff where we have a set cross another set, and that'll be the set of all ordered pairs that we can make from elements in those sets. So here's an example, and then by far the most common example we'll see will be something like r cross r, or we will often call this r2. Right? That's just the regular old Cartesian plane, where you have graphed things since you were in probably fourth or fifth grade, where you plotted points on a graph. That was just working in R2, although you didn't know that. You can work in something like n cross n, for example. Those are the points in the plane where the coordinates are both positive integers. Right? So n cross n would be the first coordinate would be a positive integer. The second coordinate would be another positive integer. So it would be like the dots on graph paper, right? At least in the first quadrant, because this is n cross n, they would all be positive numbers. Okay? So a relation is a subset of the relation between sets A and B. It's just a subset of A cross B. And we'll usually denote a relation by a, number by some letter, typically something like R, which is awful boring, which stands for relation, but that's okay because at least it sort of makes sense. Okay, what in the world does this mean? This definitely needs an example. So here's an example. Suppose that A is the set of all the students in a class, and B is the set of all the tables that you have. And of course, every student then has an assigned seat at one of the tables, and R could be the relation that matches students to their table. Okay, so back up for a second. What's A? The set of all students. B is the set of all tables. A cross B would be the set of ordered pairs, where you have a student in the first slot, a table in the second spot. And that would be all possible combinations of those would make up A cross B. R would just be the subset of that actually matches reality. In other words, that actually contains students with the table they sit at. For example, suppose that George comma table 3 was a member of this relation. That would mean that George sits at table 3. Okay. Okay, so this is a little weird, right? And I said, and a little abstract, because we're not used to thinking maybe about relations, but this is language we'll need when we talk about functions. So if you have an ordered pair, say x comma y, that is an element of a relation, then more commonly you'd write that as like x, then r, and then y. And you'd say that x and y are related by r. So if you had George r table 3, that'd mean that George sits at table 3. So one of the things that I'm sort of duty bound to say because I'm a mathematician, when I talk about relations, is to at least define what an equivalence relation is. So an equivalence relation is a relation that acts like equals does. So we call it an equivalence relation. So somehow or other it's like a kind of something, kind of like equals. It has to have these three properties. So for every x, y, and z in the set S, by the way, when I say a relation on a set S, notice that I didn't have an A and a B, I just have one set. That's because we're thinking about this as a subset of S cross S. So it's a relation of on a set S, it's really a subset of S cross itself. So X, Y, and Z are both elements of the set S, and they get to go in because they're element of the same set and it's S cross S. Then you can have X and Y on either side of the R. Okay. Okay, so it has to have three properties to be an equivalence relation. First, R should be reflexive. That means that X should be related to itself. Now, if you think about equals again, that's exactly how things work, right? An element or a number is equal to itself. That's kind of the point. Right? So, reflexive is the first property. Symmetric is the second property. That says that if X is related to Y, then Y is related to X. So, XRY implies that YRX also exists in this subset of S cross S. So again, that's a lot like equals, right? If one number is equal to another number, then it doesn't matter which one you write first because they're equal. Third thing, this equivalence relation, if it's going to be an equivalence relation, should be transitive. That means that if x is related to y is related to z, then x should be related all the way over to z. And again, obviously, think about what this would mean if the r were actually equals. If x was equal to y was equal to z, then of course x would be equal to z. Okay? Which is lots of other relations that are equivalence relations besides equals. But the point is, an equivalence relation ought to act like equals does. That's why we have it the name. Now, not everything is transitive, of course. And my favorite example of a relation that's not transitive is college football. Okay? This is what makes college football interesting and fun, and lots of arguments get inspired over the fact that winning a college football game is not a transitive event. Let me explain what I mean. So it is not at all uncommon to have, say R is a relation that the first team beat the second team. So it's not at all uncommon for Team A to beat Team B, right? Then Team B to go and beat Team C, right? So then later in the year, when A beats C, you would obviously, or A plays C, you would expect that A would beat C, right? Except they don't, right? This is extremely common. And then how do you make a ranking out of that? And the answer is, well, you fight and argue over it, and and everybody argues about who's really the best. Okay, so as I said before, equals on the real numbers is an equivalence relation. Something like less than or equal to is not. The reason is it's reflexive, right? Because a number is less than or equal to itself. And it's transitive because if x is less than or equal to y, and y is less than or equal to z, then of course x would be less than or equal to z. But it's not symmetric because you can't flip it. If x is less than or equal to y, that doesn't automatically tell you that y is less than or equal to x. In fact, that's generally not true. Um, Here's another relation that's not a math. Well, I mean, it is math because math is everything, but it does involve numbers. So consider this relation that someone is enrolled in a class with, okay, on the set of all tech students. Okay? Well, is it reflexive? Well, are you enrolled in a class with yourself? Yeah, you could consider that you were enrolled in a class with yourself, so that'd be reflexive. Is it symmetric? Well, if I'm enrolled in a class with you, then you also have to be enrolled in a class with me, so yes, it'd be symmetric. But it's not transitive because one person could be enrolled in a class with somebody, right? They're both taking the same biology class. Then person number two, right, might be enrolled in a class with person number three. Say they're both taking Spanish together, right? Then it does not at all imply that the first person and the last person are both in Spanish together or enrolled in any class together. So this is definitely not transitive. So that would not be an equivalence relation. On the other hand, if we want one more example of things that don't have numbers, look at the set of all people and consider the relation has the same birthday. So that is an equivalence relation because you obviously have the same birthday as yourself. If you and another person have the same birthday, then it doesn't matter which order you say it in, right? I have the same birthday as you, you have the same birthday as me, it's the same thing. So it's definitely symmetric. And of course, it's transitive because if If you and I have the same birthday and you and someone else have the same birthday, then me and that other somebody else will have the same birthday. So it's definitely an equivalence relation. One thing that's interesting about this example, though, is it lets us introduce equivalence classes. But equivalence classes partition their sets up into equivalence relations will partition the setup into equivalence classes. Okay, what does that mean? What it means in this example is kind of obvious, right? If you think about this, what all possibilities are there for people having the same birthday? Well, there's 366 if you count leap year, different possible days in the calendar. So there are 366 possible days I could have had my birthday on, and everybody with the same birthday is equivalent to me. So what this equivalence relation does is it takes all of the people and partitions them up into 366 equivalence classes based on their birthday. So, there's one equivalence class for January 1st. That's all the people whose birthday is January 1st. There's another equivalence class for January 2nd. That's everybody who has their birthday on January 2nd, and so on. So, another example that those of you who are taking the geometry class that we also teach, designed for future teachers, will have seen similarity before. Remember, two figures are similar if you can scale one and rotate it and translate it, and they match up. So similarity is an equivalence relation. So is congruence. Right? Well, congruence is slightly different than similarity because you have to be able to rotate or translate things on top of each other, but you can't scale them. Okay, so what does all this have to do with functions? That's a great question, and we'll find out in our next video.